Hi, everyone. My name is Luke Kim. I'm the founder and CEO of Spice AI. We are a data and AI infra startup here in Bellevue. We help customers like Twilio and Barracuda build data-intensive applications and agents, and we're the creators of a open source project called Spice AI, which you can think of as a data and AI acceleration engine across disaggregated storage. And it's built in Rust on DataFusion, Ballista, Arrow, and Vortex. So I wanted to start this talk talking a little bit about some of the changes we see within the industry. And so if you think about what we've done essentially over the last 10 years, is we've had these centralized data systems, Snowflake, Databricks, BigQuery, take your pick. And then we have applications, agents, notebooks, services pointing at these things, right? And this has worked really good. We've got lots of good gains out of it. And then what we've normally done here is get data into it. And so we have to like ETL stuff into it and build a bunch of pipelines into it. And this, if you think about Conway's law, where your organization meets, or your architecture meets your organization structure, or vice versa. What happens, when that worked really well when you had a centralized data platform team who built a bunch of stuff and you had satellite feature teams, and you kind of had the same model. And so you kind of had this analytical set of systems. Now, that was kind of the SaaS era. We're coming into the agentic and AI era. And in this era, instead of having maybe one central team with one or two AI use cases across the whole company, we are being asked to build AI into every feature, into every product, into every team. And instead of having maybe tens or hundreds or thousands of dashboard users, you're going to have now many more agents that operate not just 9 to 5, but 24/7, every day, on a schedule, on a loop. And these agents need access not just to analytical data, but they need access to a whole bunch of different data to actually be accurate. Otherwise, you don't get good quality agents, right? You get garbage in, garbage out. So what we'll see, essentially what we're seeing, is you need access to both your analytical systems and your operational data for these things to actually be useful. And you see this with like Lakebase, and you see this with Duck Lake and a bunch of other systems. But you now have this much different query load where instead of having a couple of people, you have a whole bunch of agents all trying to hit both your analytical systems and your operational systems 24/7, doing all types of crazy shit. Whoops, can I say that here? And not only that, you probably don't actually want to give your agent direct access to your data systems. There was the lovable hack just a couple of days ago, which was because they didn't do poor RLS. RLS is a great depth in defense strategy, but it's often hard to get right. And so now you have many more agents doing a whole bunch of stuff on your database. You probably don't want to give it direct access to it, and you probably don't want to rely on just one method of authorization, which is why the policy stuff is really cool. So yeah, humans don't let humans give agents direct access to the databases. So we're kind of seeing these patterns where now we just go from these larger analytical centralized systems to much more operational and analytical, from ETL to more distributed and federated. So instead of having a whole bunch of pipelines going to a central system, every team essentially needs their own data stack. And to do that and access the data you need more federation. But you also need sandboxing and isolation, and often physical isolation. And you have this kind of, much higher scale. So you see, I think GitHub said, they have more commits in the last 3 months than they've had in like the last year because of all the agents. And so how do you make all of this scale for all this new workload as well? And so we kind of think that every agent should get its own data stack. So instead of having a centralized data system where everything points to, now every agent and feature and product somewhat gets its own data stack. And we started off in using this with DataFusion and using DuckDB as some acceleration mechanism around this onto object store, essentially. So that worked pretty good for a little while. And so we essentially built this whole engine on it. It's got these core primitives for data, search, and AI. And you could encapsulate essentially a bunch of stuff that you would get in the modern data stack in search and retrieval systems and AI systems. And you could give every agent, every application their own stack, essentially. But there's a problem here. You reach this single node ceiling. And so not only do you want to give every agent direct access very fast, but it still needs to have access to your whole historical set of data, right, for it to be useful. In DataFusion's great engine, but it still has single node limits. DuckDB does not scale very well beyond terabytes, and it has crazy memory requirements. And you still want centralization for a lot of things, like ingestion, for example, and writes. You don't necessarily want to ingest across every agent ingest their own data. And so essentially, we wanted to go to a distributed nature, but we also still need the centralized nature. So what we really want here for this agent world that we believe essentially is this cluster sidecar architecture, which is similar to what Scott was talking about with his policy. And so here is where your agent essentially has low latency, high performance access to a sidecar that has a full query engine, full search engine, full inference engine in it, but can delegate queries to a centralized cluster that still protects you from all your backend stores, federates across them, can centralize writes, and so forth. And so now you get this very fast, low latency working set, which is often less than 1 terabyte, and then you can go from terabytes to petabytes for your cluster on demand. And these map really nicely to DataFusion and then Ballista, which I'll talk about. And Ballista is built on DataFusion, but it's kind of the distinction there. So, am I going for time? Yeah. So, DataFusion Ballista essentially is a compute platform. It's also built in Rust, or built on top and powered by Apache DataFusion. And so you can kind of think about Ballista as going from single node in DataFusion to multi-node, or if you're thinking about in terms of query engines, like going to Spark, for example. And so it has this basic architecture where it has a scheduler. You can kind of think about this as a driver in the Spark sense, or maybe like a coordinator in Dremio or something like that. And then you have multiple sets of executors, which it can get distributed jobs, essentially, or tasks. These are called stages within Ballista. And then you will have essentially these shuffles where it can shuffle data between these and between stages. And then it'll combine all those things and collect them all back up and give you the arrow results, essentially. And because it's all arrow native, it works really well within the Arrow and DataFusion ecosystem. And then just taking straight off Ballista's page here, there's quite a big speed up over Spark in a lot of cases. And so basically, Ballista lets you go to do something like this. On the left is a kind of a basic DataFusion plan. And then on the right, you essentially can take, and this is just like a basic select count over Amazon reviews. It's able to break it up into multiple stages. And then within each one of those stages, it can break it up into multiple partitions. So you can see there's 16 partitions in each. And then for each of those stage partitions, it can distribute them across multiple nodes that, or many of these executors. And so that way you can get it parallelize these queries, and it will be able to do these disk-based shuffles between them, so it'll write essentially intermediate results between these stages, pick them up. That will also help for resumability. If the query breaks halfway, you can kind of resume it, and you get that parallelism. All right, so give a bit of a demo about how some of this stuff works. So, and I was just, I had this, I thought it was interesting that you did the talk on Scylla because I literally just have a PR to add that into Spice. So this is Spice Cloud. One thing I'll just say here is that Spice is fully open source. You can run it completely on your own machine, everything from a Raspberry Pi all up to a cluster. We have a YAML syntax for configuring it. And so this is a very basic, what we call a Spice pod. So we have that same Amazon reviews set. We're actually using Delta and Databricks here to point to it. We can federate to, I think, 35, maybe 40 sources right now. And so we essentially have two data sets, one which is a standard data set pointing at directly at Delta, and two, we have what's called an accelerated data set, and I'll talk about what that means in a moment, accelerating our engine called Cayenne. And then this is automatically partitioned into 3 buckets based on product ID. A bunch of other stuff here, which is around the columns, but one thing I wanted to note is that you can automatically annotate this with embeddings, or saying that this column will use embeddings just with this syntax here. We have 2 embedding models that you can plug in here, and then an LLM model here as well. So if I come across to here, this is a fairly standard query interface. I don't know how to make that. So this is Spice. It's just a playground query interface for SQL. And here we have this Amazon reviews data set. And if you start this run right now, and this is actually going to run it on a single node, what your typical DataFusion would look like. And it'll take about, I think, 15 to 17 seconds. There's 2 kind of queries here. We're taking reviews from 2012 and reviews from 2015. And we're doing a bunch of aggregations over them to find out how a product review changed over time. And you can see that this takes, it's about 100 million rows. So not that small of a data set. It takes about 22 seconds to do this aggregation and figure out essentially how the reviews have changed from 2012 to 2015. Now, if we were to look at the explain pattern real fast, then you can see here that it's able to break up the 2 subqueries into 2 trees here. And if you come down here, you can see that 63 Parquet files on one side and 75 Parquet files on the other side. It's able to push down all the predicates and the filters, come back up, get the result, join them together, and then do a bunch of stuff, filtering and sorting and giving us our result. If I come across to this tab here, this is going to run on Ballista. And so what we have here is a cluster where we have 2 schedulers and 3 executors. And so it's going to split this across across all of those nodes, essentially. And so I'm going to run the Ballista query here. And this will finish in about 7 seconds. So it's about twice as fast. And then if you look at the explain plan here, then you'll see that here we have this new distributed plan, essentially. So we have a physical plan, but if you scroll down here, we have this distributed plan. And you can see now this is how it breaks it up. So we have 2 stages, 1 stage here, and it's a resolve stage, means that it can basically run immediately. And so this is that first CTE. And then we have a second stage here, which is the second CTE, and they can both run. And then when they both run, it's going to go gather all that data. Here's the Parquet files, put it into a shuffle. And then if you look coming down to the bottom here, you'll see this is unresolved shuffle. So it's waiting on the files. And then it'll do the same thing. You'll go find the hash join here. It's got the hash join here. It's going to take them together and bring us our result back. So we've gone from about 17, 18 seconds to it was about 7 seconds, so about twice as fast, by being able to distribute these across multiple nodes. But we can do better. So with Spice, what we have is this concept of acceleration. You can kind of think about acceleration as like a materialization, but a little bit more flexible because we store it normally within a queryable format, like embedded database like DuckDB, or something like a columnar format that's queryable. And so if I run this with acceleration, we can do that same 100 million row query. We can do that in about 2.38 seconds. And so what we're doing there essentially is able to partition the query, but also partition the acceleration and store the acceleration on each one of the executor nodes. And so when we do the query through, it can read directly the data off each one of those nodes in a partitioned way instead of out of object store each time. And so you can get some really, really high speed ups. And if you can imagine what I talked about before, when you have all these agents doing a whole bunch of crazy stuff, if you can actually materialize and accelerate the data, and you can kind of let them go to town on your data set, even very large data sets. So if we look here at the explain plan from this is a little bit different. So we essentially use Ballista to manage the cluster state, but we're doing a synchronous query directly from the schedulers to the executors instead of using a shuffle. So that's how we can make it even faster here. And then what we've done is, so if we come down here, you'll actually be able to see, distribute the queries across each one of the nodes at the end. And we're actually talking to these nodes using FlightSQL. And I'm sure some people in the audience will say, hey, could that just be Substrate or DataFusion distributed? It could be. And we're going to be integrating that soon. And so essentially within Spice, you have both the ability to do a large-scale distributed query using shuffles or a more synchronous query that doesn't use intermediate shuffles and just uses node-to-node communication. So yeah, that is a look at Ballista and distributing queries across multiple nodes. What can we do with this now? Well, one thing we might want to be able to do is take all that data and embed it for vector search. And so we have within Spice the, I'm coming up on time here. We have a UDF that we've created called embed. So we can just give it a column, and you saw the embedding models that we had before, and then we can just run embeddings across all of those. Here, I'm going to just run it at a 100 limit, and so you can see it's pretty fast. I'm not going to do the whole data set because that'll take some time, but one thing I did want to show is that if we look at the plan here, it's able to essentially go fetch all the data, but then only automatically optimize to run the embed on the actual scheduler, just on that last 100 results. But if I was to do the explain plan on the whole data set, what you'll see is that the planner will automatically run the embed on and push down the embed to all of the executor nodes. It's kind of hard to see here. This is, yeah, so you can see wherever the embed is there. So the embed gets pushed down to each one of the actual stages and nodes. So it's able to figure out where the best place to run it is. And then once you actually have embedded a whole bunch of stuff, what might you want to do with it? Well, you could run vector search over it, for example. And so here, I'm going to skip over some of this and go faster. But here we have distributed vector search across multiple nodes using those executors. And you can see that this should finish pretty fast, about 10 seconds. Oh, I know why. I hit the wrong thing. Let me just refresh that. Yeah, so here you'll see, so there's vector search across multiple nodes. And then, we can do a whole bunch of different things like re-ranking across them. And then all of this will get pushed down essentially to each one of those individual nodes. Then vector search is just, again, a means to the end. What might you actually want to do with those results? Finally, we have here a AI UDF that we've built. And so essentially, we can take the results of that vector search and automatically pipe it into LLMs here. And so, and again, run that distributed across each one of these nodes. So each one of those nodes is actually doing their own call to essentially a hosted LLM, which in this case is OpenAI. And it's running slower. Yeah, so there you go. So essentially, each one of those calls, it's able to pipe the results of that search back into the LLM. And in this case, we're categorizing the Amazon review for each mobile app and giving it a rating, essentially, and then converting it to pirate speak. So yeah, that's a really quick overview of some of the things you can do with Apache Ballista. So real quick, no, we're coming out of time. One thing that we've been able to do here is write an optimizer rule to ensure that when you run the embed on a distributed node, executor node, it'll actually automatically load the embeddings model on that node and ensure that it has all the things it needs to run so that it can actually do the embed on that actual node and push it down. And so it'll load it the first time, and then once it's loaded, it's just a no-op, and you can just use it, for example. The next thing that we've been able to add to Ballista is that it's single scheduler only by default, which means if that goes down, then you're kind of posed. And so what we've done is added the ability to have multi-active schedulers based off of object store. And so we essentially have a cluster.json, which uses optimistic conditional writes with optimistic concurrency for all the cluster states. So we can have multiple schedulers running at any one time that share a pool of executors, and anyone can go up or down, and we can continue to run queries. Turbo Puffer is another example of kind of using object storage to do this type of synchronization. And then finally, we got some of those speedups. We use Vortex quite heavily, which is another columnar format. And it's based on a whole bunch of research, and it's able to do essentially per column encodings and a whole bunch of stuff. That's really good. It's a whole talk on its own, so I won't go into it. But it gives you a whole bunch of speedups, and that's how we got to that, kind of very 2-second, 3-second query. So finally, a couple of things we built on Ballista. We built this object store-based multi-active schedulers. We built a whole bunch of accelerations and codecs, like the embeddings, embed vector search and text search, which get sent across to the executors. We were able to add in different types of shuffle backends and formats. So not just use arrow IPC, but you could also use Vortex. We could put Lance in there, for example, for a shuffle formats. We added a full suite of observability in there that's not there by default, and then a whole bunch of ways to make it go faster, like control streams and job state streams and so forth, as well as full enterprise-grade MTLS across all the nodes. And then one thing you saw there is we added explain format tree to Ballista as well, which is kind of nice. So last slide, which is the first thing I showed before was running Ballista. It was like 2.6 times faster than Spark. What we've found is like the standard TPCH and ClickBench benchmarks is great, but they don't really handle how you do continuous ingestion and mutations over time while you're querying, which is what we really care about when it comes to these real-time systems. And so we essentially built a thing called SpiceBench, which will do that. It'll take standard data sets and it will continuously ingest them into your system while it continuously queries, and it measures end-to-end latency time, it measures query time, and so forth. And it will also do mutations as well. So it'll handle not just appends, but deletes and updates. And so when we ran all of this together on TPCH SF10 with continuous ingestion and mutations, we got quite good results. These are fairly early, but quite good speedups as well compared to essentially Spark and SQL Warehouse, essentially. And then SpiceBench is open source, and so we're trying to get more and more systems to utilize that and be able to kind of test the end-to-end latency here. So that's it. That's Spice. Super easy to install. couple of seconds to get onto your machine. Love you to give us a star to get us over 3,000 stars. And that's it. Thank you. Sorry I went over time.